Today, we will use the Fourier transform to move from raw measurements to hidden frequency structure in Python. At first, we need import scientific tools for numerical computation, visualization, Fourier analysis, and signal filtering. Each library becomes a specialized scientific tool. A digital signal must be observed through time. The computer defines the sampling rate, duration, and thousands of discrete time points. Continuous reality is converted into measurable numerical samples. The foundation of signal analysis has now been created. Inside the signal, two hidden oscillations are combined together. A strong 50 Hz wave and a weaker 120 Hz wave overlap in time. Mathematically, complex signals are often built from simple sine waves. What appears complicated is actually a hidden orchestra of frequencies. But real-world measurements are never perfectly clean. Random disturbances from sensors, electronics, and the environment introduce noise into the system. The smooth oscillations become buried beneath apparent chaos. The true structure is now difficult to see directly. He, scientist, now examines the waveform in the time domain. At first glance, the graph appears irregular and confusing. The hidden oscillations are masked by random fluctuations. Visual inspection alone cannot easily reveal the underlying frequencies. Now, the computer enters frequency space. The Fourier transform compares the signal against rotating waves of many different frequencies. Instead of analyzing time directly, the system searches for oscillatory structure. Hidden patterns begin emerging from the noise. Digital Fourier transforms naturally produce both positive and negative frequencies. Because real signals contain mirrored information, only the positive half is physically useful. The scientist removes the redundant portion of the spectrum. The hidden frequency structure becomes simpler and clearer. The frequency domain graph is now displayed. Suddenly, strong peaks appear near 50 Hz and 120 Hz. The invisible oscillations hidden inside the noisy signal become visible. The Fourier transform has revealed the signal's hidden ingredients. The computer now searches for the strongest oscillations automatically. Small fluctuations are ignored while dominant peaks remain. The output identifies the true frequencies inside the signal. The hidden structure has now been successfully detected. Now we remove unwanted high-frequency noise. A mathematical low-pass filter is carefully constructed. Meaningful oscillations are preserved while rapid disturbances are suppressed. Mathematics becomes an instrument for cleaning reality itself. The filter is now applied to the noisy measurement. Random fluctuations begin fading away. The meaningful oscillations remain visible and stable. The original hidden structure gradually reappears. The computer now compares the noisy measurement with the reconstructed signal. Two different worlds become visible, apparent disorder and underlying order. The cleaned waveform reveals the structure hidden beneath the noise. Fourier analysis transforms confusion into understanding.